So, last class we have discussed that from the description of the problem, how one can formulate the multi-objective optimization problem in mathematically. Then we have discussed the what is called the preliminaries of vector calculus. The function is given which is a multivariable function, how to find out the gradient of a vector, and simultaneously we have found out the gradient of vector. If you once again differentiate with respect to x, then we have seen it becomes a matrix, which matrix is a symmetric matrix and its dimension is n cross n, where the n is the number of variables involved in that function and that matrix is a symmetric matrix we have seen. And with a example we have seen how to find out the gradient of a vector. Today we will just discuss how to find out that Hessian matrix. That means, if we have a differentiate that function twice, second order differentiation you do it, you will get an Hessian matrix. How to compute that matrix? So, let us take one example. That example, same example what we have considered last class for a to find out the gradient of a vector. So, the example calculate the second derivative of the function f of x is equal to x 1 square plus twice x 1 x 2 plus 3 x 2 square plus 4 x 1 x 2 x 3 plus x 3 square. Calculate the second derivative of the function at point x is equal to x star. Here the dimension of x is 3 cross 1. Okay. That means, this has a x 1, x 2 and x 3, and these values are given 1, 2, 0. So, in order to find out the Hessian matrix of this function, that means, the gradient of this function once again if you differentiate, agree, then this is called the second derivative of this function for a multivariable function. So, that can first you have to find out the gradient of this function f of x. That last class we have found out f of x value at x is equal to x star. First you let us call you find out the f of value f of x gradient of this one is nothing but a del f of x with respect to x 1, then del f of x with respect to x 2, then we have to find out the del f of x with respect to x. Since we have a 3 variables are there, function is a this function f of x is a function of x 1, x 2 and x 3. So, this if we differentiate this function with respect to x, last class we have seen it is 2 x 1, recall this expression x 2 plus 4 x 2 x 1, then differentiation of f of x with respect to x 2, that will come 2 x n square plus 2 x 1 plus then 2 x, this is x 1 with respect to x 2, this is a bit, this is sorry, this is 2 x 2, sorry, this is 2 x 1, then 6 x 2, then 4 x 1 x 3, and then if next is if you differentiate f of x with respect to x 3, then is a function of these two terms, a function of x 3. So, it is a 4 x 1 x 2 plus 2, this is a cube not square, please see, recall the last x function, it is a 3. So, 3 x 3 square. So, this function you have to once again you have to differentiate with respect to x. That means, vector this gradient of this vector, once again we differentiate with respect to x. So, if you differentiate this with respect to x, that is denoted by this symbol f of x. So, this one we have seen it is like this way. So, del f of x del x 1 square, del f square of x del x 1 del x 2 and del square f of x del x 1 del x 3. Similarly, this is del square f del x 1 and del x 2. This will be del square of f x x, this is del x 2 square, del square of f x, then del x 2 del x 3, and last of this one is then del square f of x is equal to del x 1 of 3 del x 3, then del square f of x is del x 2 of del x 3, then del square of x is equal to del x 3 square. So, this is a 3 by 3 matrix and this is a symmetric matrix, because A 1 2 position, A 1 2 position is A 2 1, A 1 3 position is 3 1 and A 2 3 position is A 3 2. These are all identicals, these off diagonal positions of this one. So, one has to calculate, since we know the, if you see this one can calculate this one, we know del f of x with respect to x 1, that value we know, this value is 2 x 1 square 2 x plus 2 x 2 plus 4 x 2 x 3. So, once again you differentiate this with respect to x 1, that value will be coming 2 only. Similarly, you differentiate this del of x del x 1, already you have differentiate with respect to x 2, then it will come 2. There, what is this? There, with respect to this is a 2 plus 4, it will come 4 x 3. Agree? Then again you can differentiate del f x plus del x 1 del x 3. This one with respect to x 3 you differentiate, that will come your 4 x 2. Next is, we know that del f of x in del x 2 expression, this is expression with 2 x 1 plus 6 x 2 plus 4 x 1 and x 3. So, you differentiate del f of x with respect to del x 2 square. So, differentiate with respect to x 2. So, that will come, if you 6, then del L square f of x del x 2 and del x 3. So, differentiate this thing with respect to x 3. So, that will come 4 x 1. So, only left is now differentiation of del f of x with respect to x 3. We know this expression is 4 x 1 into x 2 plus 3 x 3 square. So, now you differentiate once again this one with respect to x 3. So, this will be del f of x del x 3 square will be equal to 6 x 3. So, put these values in that matrix, this one, and find out this matrix value. So, you have already calculated these values, all partial derivatives, second order partial derivatives, all these elements we have calculated earlier. So, now if you put these values there, then our matrix, which we will call Hessian matrix of del square of f x, is coming is 2 plus 4 x 3 plus 4 x 2, 2 plus 4 x 3 plus 6, 4 x 2 x 1, then 4 x 2, 4 x 1 and 6 x 3. So, now you have to find out the Hessian matrix at a point That means, we have to find out the Hessian matrix, that matrix will be at a point x is equal to x star, and that matrix dimension is 1 3 cross 1, and that is given value is x 1 is 1, x 2 is 2, that is 0 0. If you put in this expression, that is 2 as it is, this x 3 is 0. So, this will be 2, then x 2 is your 2, that will be 8, agree, then x 3 is 0, 2, 6 as it is, then x 1 is your 4, this x 2 value is 2, 8, that is x 1 is 1, 4, then x 2 is 0, this one. So, this is our Hessian matrix, this matrix is Hessian matrix. That means, if you differentiate the gradient of a vector once again with respect to x, that matrix you will get a Hessian matrix, and that matrix for this particular example, when you use x, the value of at point x result x star is 1 2 3, this is our Hessian matrix, and it is a symmetric matrix of this one, and symmetric you can write it. Okay. So, next is, before we go to this our what is called in order to find out the optimum value of this function, which is a function is a several values of x 1 x 2 dot dot x n, let us call the function f of x is a function which is a function of x 1 x 2 dot dot x n. In order to find out the optimal value of the function at a point, then we must have few more mathematical preliminaries. So, that is next is quadratic function. So, let us call that we have a function with two, if we have a function, we have a function with two variables x 1 and x 2, x 1 and x 2. The quadratic form of the function is a x 1 square b x 1 x 2 plus c x 2 square. It can be a in addition to the constant term plus the linear terms. Okay. Let us call for the time being is this one, it is a quadratic function. Then this quadratic function, our problem is this is the quadratic form. So, this quadratic form one can express into a matrix and vector form. So, let us call this is equation number 1. So, one can express the equation 1, one can express the equation 1 as like this way, f of x equivalently one can express like this way, this equal to x 1 x 2. We have considered for the 2 variable case, then we extend for n variable case. This we can write it like this way. You see this, what is the coefficient of x 1 square is a, that will write in a 1 1 position of the matrix which are going to form. So, that is a. Then a 1 2 position is will be your our this matrix a 1 2 position means 1 2 position coefficient is b, that we can write it here. Then 0, then what is the coefficient of x 2 square, that we will write it a 2 2 position, that means c into x 1 and x 2. So, if you just do the operation matrix vector operation, then whatever the results will get, and with the row operation with this one we will get exactly whatever the function is given. This is one choice, or one can write it like this way: x 1, x 2, then a 0, b, c. The A12 position or A2 position I have just written here, this one, and this is x 1 and x 2, and also this, if you do the operation, you will get exactly whatever the function is getting. Now, one can write also like this way: there are infinite number of choices are there to put that matrix, this matrix. So, I can write it here, because x 1 square coefficient is A. So, that will remain in A11 position. X 2 coefficient, x 2 square coefficient is C, that will remain in A22 position, and this is x 1 x 2 coefficient, and this is also one can write it x 2 1 position, that this x 1 coefficient, x 1 and x 2 coefficient can be distributed with these off diagonal things, that sum must be equal to the coefficient of x 1 and x 2. So, I can write it also like this way, there is no problem if I write it minus b, 2 b, and c is like this way. So, you see, if I write this expression, it will A1 A x 1 square, then c x 2 square, then I will write it here minus b x 1 x 2, again there is a 2 b x 1 x 2. So, if you simplify, it will come only b x 1 x 2. So, this is one. The most of the cases it is selected the matrix P is, or if one can write it in symmetric matrix form. X 1 x 2. Now, see how I am writing in symmetric matrix form. This one, coefficient of x 1 and x 2 is b. The half of this b by 2 I will write in 1 2 position, and b by 2 I will write it 2 1 position. So, it will be a x 1 square a, x 1 square coefficient is a, x 2 square coefficient is c, then coefficient of x 1 is b, I divided it into 2 parts to make the matrix symmetric. So, it will be a b by 2 and b by 2. So, you can easily realize that we have a infinite number of choices, but this choice has a, I mean, most popular choice of this one, because we can conclude something from if the matrix is symmetric matrix regarding the function. Okay. So, our conclusion is P is not, if you consider this matrix is P, or this is also P, this matrix also P, this matrix of P, P is not unique matrix. To represent the function, quadratic function into this form. What form? This I can write it, if you consider x 1 x 2 is a vector form, you see here I can write x transpose, this is vector. So, it is row vector. So, x transpose I can write it that P into x, this is 2 cross 1 for this example. Similarly, I can write x transpose, but here P is different, agree, this form. Here also I can write x transpose P x of t, but P is different. But all these cases it is same as, equivalently same as function of x 1 and x 2, and in this case P is symmetric matrix. In this case P is symmetric matrix. Is not unique. So, let us say that in general we have seen that out of the, for this example, out of the 4 P matrices which will give the exactly same value of expression of f of x 1 and x 2, out of this one is we have considered the symmetric matrix choice. So, in general for n variables, function is a n variables, f is a function of x 1 x 2 dot dot n x n. a quadratic form of n variables n cross 1, which is a n quadratic form of n variables. What we can write it? F is a function of x 1, x 2 dot dot x n, which in vector form we can write x of n, whose dimension is n cross 1, is I can write it this is equal to x transpose p x, agree, where x is equal to x 1, x 2 dot dot x n whole transpose, means it is a column vector of dimension n cross x is a dimension n cross n. Suppose the P is not symmetric, suppose P is not symmetric, suppose P which is n cross n, this is n cross 1, this dimension will be n cross n. Suppose P is not symmetric matrix, one can always suppose this one f of x, just now we have written x transpose p n cross n into x whose dimension n cross, and p is not symmetric. And look this expression, this is a scalar quantity, the function is a scalar quantity this. So, I can always write, there is no harm, I can always write that x transpose p cross this x and half x transpose p x, because suppose this constant it is 10, I can put it here 5, here 5. So, it is a 10 ultimately scalar. So, this quantity is scalar. So, this further we can make it after some manipulation of this one, I can write it p into x plus, since it is a scalar quantity, agree, then I can take the transpose of that one. So, this x transpose p x, that transpose here. Since I have considered it is not a symmetric matrix, that will be a p transpose. Note how I have written this one. If A is a matrix of dimension m into p, B is a matrix of dimension proper dimension p cross, let us call n, C is a matrix whose dimension n cross r, agree. So, we can multiply A, B, C, this, you see they are with proper dimension. If this is this, agree, then this product, if I resultant of this matrices product matrices after multiplication, if you take transpose, this is we can write C transpose, reverse order you write C transpose, B transpose, A transpose, and this property I have used it here to take the transpose of that one, taking the transpose of that one. Or you can say, just you can forget about this, I am now taking the transpose of that one. So, this equal to, now I can write it x transpose p x plus half, this is half is there, half, then x transpose, you can say this is A, this is B, this is C, C transpose means x transpose, then B transpose, P transpose, that this transpose of a transpose, that means x. So, if you make the simplification of this one, half you take common, then you can write x transpose common, then you write P of P transpose by 2, sorry 2 you push it inside, agree, then x. So, this matrix is a P is a, that is our non symmetric matrix, take transpose of this one, agree, and divided by 2, and this matrix we know if A is a matrix non symmetric matrix, if add with A transpose, result is a symmetric matrix. and we are dividing by scalar by quantity 2. So, all elements of P plus P transpose will be divided by 2 only. So, this is a symmetric matrix. And you see this we have derived from this expression. Okay. So, x transpose P x, if P is not symmetric, we can write it this one x transpose P plus P transpose by 2 into x, where this matrix is symmetric. That is, this matrix is symmetric. So, whatever the results we will get it, agree, the expression in terms of what is called f of f function f, which is a function of x 1 x 2, the same expression we will get it here also. That means, x transpose P plus P transpose by 2 into x, same. But only the advantage is we are getting this matrix is now become a new matrix, which is a symmetric matrix. But scalar, this function value, scalar value expression in terms of x 1 will be same expression as this one. So, this is our conclusion of this one, that even if P is not symmetric, I can make the x transpose P plus P transpose by 2 into x is an expression whose values are same as these values in terms of x. So, let us call now we define some of the function, positive definite function, definition of positive definite quadratic function. So, let us call we have a nth order quadratic function is there, f of x is a function of n variables, which is in general we am writing p 1 1 x 1 square, p 1 2 x 1 x 2, p 1 2 x 1 x 2, then p 1 3 x 1 x 3, and dot dot we have n variables are there, p 1 n x 1 x n plus p 2 1, let us call this is x 2 x 1, p 2 2 x 2 square, p 2 3 x 2 x 3 plus dot dot p 2 n x 2 x n. And in this way, if you consider the all these things, last term of this one will be p n n x 3 x n square, agree, which we can write it into matrix and vector form. Is a matrix and vector form. This dimension n cross n and this dimension n cross 1, where p is, see clearly p 1 2 p 2 1 is not a symmetric matrix. These two things are not same. A 1 p 1 3 and p 3 1, third equation will come, is not a same quantity. So, you will get a non-symmetric matrix, non-symmetric matrix, agree. So, our definition of positive definite matrix is that first the function f of x, which is equal to x transpose p x n cross 1, this is said to be positive definite bracket. When you will read the bracket, we will read all in bracket terms, or we will get positive semi definite quadratic function. The function will be said to be a, this function f of x means this function which you have written into matrix form, matrix and vector form, is said to be positive definite quadratic function if f of x is equal to x transpose p x is greater than 0 or bracket term will said to be positive semi definite when it is greater than equal to 0 for every x and x is not equal to null vector. When x is equal to null vector, x 1 is 0, x 2 is 0, this function value is 0. Okay. So, this will be, so I repeat once again, the function is said to be, f of x is said to be positive definite function, agree, if f of x, x transpose x, that means f of x function value will be greater than 0 for all values of x except x is equal to if it is not null vector, always 0. If it is a semi definite, the function value may be 0 or greater than 0 for every value of x which is not null vector, if it is x is null vector. So, this is the definition of this one. Then second definition of this one, that function is negative definite. Similarly, the function f of x is equal to x transpose p x, which is a, this is said to be negative definite or negative semi definite agree, definite quadratic function if f of x is a function of x 1 x 2 which can be expressed in terms of matrix and vector form, the x transpose p x, agree, this value will be, if it is negative definite, this value function value which is a scalar is always less than 0. If it is a semi definite, this function value will be less than equal to 0. It function value may be negative or 0 this. So, there is a negative for every x whose dimension n cross 1, that means n cross 1 is not equal to 0. Now, this function may be indefinite, that means a function is said to be indefinite when this x function value can be greater than 0 or less than 0 or maybe 0. So, we cannot say anything that for all values of x which is not equal to 0, the function value is either positive, negative or 0, it can be anything. So, that is called, what is called function is indefinite. The function f of x which is equal to x transpose p x is said to be indefinite quadratic function if f of x is x transpose p x is greater than 0 for some values of x, agree, which is not equal to 0 null vector, and f of x which is a x transpose p x is, this value is negative for other values of x, for other values of x which not equal to 0. So, this is called indefinite quadratic functions. So, now So, we can see next. So, we now we know the what is a positive definite quadratic function, negative definite quadratic function, positive semi definite quadratic function and negative semi definite quadratic function. Along these things in the same line, what is called definition of positive definite matrix, it is just linked with this only. Definition of positive definite matrix. So, let us call for a P which is a n cross n matrix is positive definite matrix if and only if you multiply it by P matrix, agree, whether P is a symmetric matrix or non-symmetric matrix, whether it is a positive definite matrix, you multiply it by P matrix with proper dimension, pre-multiplied by a row vector, post-multiplied by a column vector of same. So, it is a column vector, post-multiplied column vector and pre-multiplied by same vector which is row vector. Okay. So, this if this quantity is greater than 0 when x is not equal to this, then we will call the matrix is positive definite. But see, this has become a quadratic function now, x is this. So, what is this means? If P is a positive definite matrix, you pre-multiply by x transpose any vector x and post multiplied by x. If this quantity is greater than 0 for all values of x except x is equal to null vector, then we will call matrix is symmetric matrix. Agree? So, next is positive definite, you can say this, if if P is equal to P transpose, that means P is a symmetric matrix, then we will call that this P is a symmetric matrix and that symmetric matrix is, if it is greater than 0, and one thing is there P positive definite, in short it is written like this way, P greater than 0 means P is a symmetric matrix. P positive definite, in short it is written P greater than 0 means P is positive definite matrix. So, if it is a P transpose greater than in 0, it indicates that P is a symmetric matrix, but this does not indicate P is a symmetric matrix, P may be non-symmetric matrix also. So, next is the definition of positive semi-definite matrix or positive semi-definite or negative definite matrix, or you can say negative definite matrix, definite matrix, definition negative matrix is the same. The for a function P whose dimension is n cross n is negative definite matrix, that means in short it is written P less than 0 is, I will read as a P is a negative definite matrix if and only if that x transpose P of x is less than 0 when x is not equal to null vector. Again, that this is not a null vector. So, again this is a quadratic function and P may be a symmetric matrix, may not be symmetric matrix, but that P is, if it is a non-symmetric matrix or symmetric matrix, is a negative definite if this x transpose P x, which is a quadratic form in terms of variables x. X means is had as a n components are there, x 1, x 2 dot dot x n. If this value will be less than 0 for all values of x except this one. So, next is definition of positive semi definite. Again, if P is positive semi definite, positive semi definite, semi definite. In mathematically it is written positive semi definite, P is greater than 0. I will read it, P is positive semi definite if and only if x transpose P x, that is a scalar value, this value will be greater than equal to 0 when x not equal to a null vector. So, this is the definition of that one. Again is there we can also derive the definition of negative semi definite matrix. Again, definition of negative semi definite matrix. Negative semi definite matrix. So, the matrix P n cross n is said to be negative semi definite matrix. In short, it is written like this way. We will read P is semi definite matrix, negative semi definite matrix, sorry, if and only if the quadratic form, that means that matrix you pre multiply and post multiply, pre multiply by x transpose and post multiplied by x, x is a vector of dimension n cross 1. If these values is scalar value is either negative or equal to 0, this for when x is not equal to n null vector, x dimension is n cross n. See. So, this is that. Now, question is coming that there are infinite number of vectors are there exist. Then how will we check this thing, whether the matrix P is a positive definite matrix, which in turn that x transpose P x is positive definite quadratic function or not. So, there is an infinite number. The test for now the test for positive definite matrix, and this is done for Sylvester criteria. Sylvester criterion, and this is valid. Sylvester criteria you can apply only if matrix P is symmetric matrix. This is for if P is symmetric matrix, then only you can symmetric matrix. So, a matrix is positive definite or not, that test one can do by using Sylvester criteria. Again, can do using provided this matrix is symmetric matrix. And according to the dimension, according to the definition of symmetric or a positive definite matrix, we know that x transpose P must be x transpose P positive definite matrix, this must be greater than 0. Okay. Now, if P is given, P is may not be what is called symmetric. So, we can always express that one I just shown you, we can always write it this one x transpose P by 2 x transpose P plus P transpose by 2 x, whatever the value we will get it this one, and this value are exactly same. Okay. So, in other words, that if P is not symmetric matrix, we will convert into a this form P plus P transpose by 2 and then test with this matrix, which matrix is symmetric, that P plus P transpose by 2 I am denoted by Q. So, I am testing with this matrix. Agree? Q matrix, if Q is symmetric, in turn I can say this function, if Q is symmetric, x transpose P greater than 0 will be there. By using the Sylvester criteria test, I can find out whether Q is positive definite or not. If positive definite, then this will greater than 0. So, how to check positive definite matrix, that Q. So, from now onwards I will consider our P is a symmetric matrix. So, Sylvester's test for positive definite, let P n cross n is symmetric matrix. Even it is not symmetric, I will convert into a P plus P transpose by 2, that one I will consider as a P, which is a symmetric matrix. Symmetric matrix. Then Sylvester theorem tells, if it is a symmetric matrix, again P, that P is positive definite, provided first check is all the diagonal elements of P must be positive. All the diagonal elements, that means P I is equal to 1 2 dot dot n must be positive and non-zero elements. This is the first condition. If this is there, all diagonals of P is like the whatever the P matrix is given, converted into symmetric matrix like this way, P plus P transpose by 2, and then check all the diagonal matrix are positive on and non-zero. If it is so, further you proceed like this way. All the leading principal minors means determinate must be positive. So, let us note what do you mean by the leading principal minors. The leading principal minors, the leading principal minors minor of order k of an n cross n matrix is obtained by deleting last, mind it, last n minus k is the order n minus k rows and columns, last n minus rows and columns. Okay. So, this is the leading principal minors. So, let us take an example and check how this test can be done, whether a matrix is positive definite matrix or not. So, if you consider this one example, this determine the nature of the quadratic function. The nature of the quadratic function means whether the function is positive definite, negative definite, or positive semi definite or negative semi definite. This nature you have to go. So, that function is given once again. I can write into this general form, which is a function of your 3 variables x. So, I am writing dimension x, dimension is 3. So, 7 x 1 square plus 4 x 1 x 2 plus 10 x 1 x 3 plus 5 x 2 square plus 8 x 2 x 3 plus 9 x 3 square, and where we have considered x is equal to a vector consist of x 1, x 2 and x 3. 7 x 1 square, 4 x 1, 10 x 1 x 3, 5 x 2 plus 8 x 2 x 3 and 9. So, this thing I can easily convert into a matrix and vector form that you use. So, x 1 x 2 these are there, then this P matrix, this is the our this you have to fill it up from this information. I told you the x 1 square is 7. So, it will go in 1 1 position. First I will diagonal element say x 2 square is 5. So, it will come here, x 2 2 position, x 3 square coefficient is 9. So, it will come 3 3 position. Now, you see x 1 x 2 product of x 1 x 2 agree. So, you can put it here 4 here 0, but problem is I want this is a symmetric matrix. So, that I can test the Sylvester inequality condition whether P is this P matrix if it is symmetric, this value will be greater than 0 provided P is positive definite. Okay. So, this I will equally distribute between the A 1 2 position and 2 1 position. So, 4 2 2 equal. So, that it will become symmetric. Then 10, what is the x 1 and x 3 1 3 position, 5 is here and 5 I am giving here 1 3 3 1 position. Then your 2 3 position, 2 3 position is 8, this is 4 and this is 3 2 position 4. So, this is our P matrix and this P matrix is a symmetric matrix. So, if we can show if P is a symmetric if you can show the P is a positive definite matrix, means P greater than 0, if you can show positive definite matrix, then this function value is always greater than 0 for all values of x except x is not equal to null vector. So, let us say by using Sylvester inequality Sylvester criteria, then what you have to find out? First, we have to find out the leading principal minor of order 1, leading principal minor of order 1. Then what is this? Then our how many rows and columns we have to delete from the last row? You see I have written n minus k, n is equal to n 3 and order is k order is 1. So, I have to delete 2 rows 2 columns from the last rows, 2 rows and 2 columns. So, only this elements is left. So, that is 7, order is 7 and that is greater than 0. Next is leading principal minor of order 2, k is equal to 2, here is k is equal to, you can write k is equal to 1. So, this is what? Then n minus k, n is equal to 3, k is equal to 2, this is 1. Last row and last column you delete from the matrix P, last row, last column. So, you have only this matrix. This matrix is, if you see this matrix, this will be a 7, last row, last column, if you delete it, then your matrix is determinant of that one, determinant of that 7 2, determinant of this matrix 7 2 2 5, and that determinant if you see this is 35 minus 4 is equal to 31, which is greater than 0. And last, because if an order is n, I have to consider up to nth order minors. Agree? Leading principal minor of order k is equal to 3. That means, it indicates n minus k, n is equal to 3, k is equal to 3. This is no rows, no columns you have to delete. That means, you have to take the full matrix what is P is given. So, determinant of that matrix you have to find out this one. That matrix is 7, see this one 7 2 5, 2, 5, 4, 5, 4, 9. So, the determinant is you have to find out. So, that value, if you find out this determinant, you will get this determinant value is, you know how to find out the determinant value is greater than 0. So, according to the Sylvester theorem, if you see this one, he is telling first what if the matrix P is there, if it is a symmetric matrix only, our case we have formulated this thing in the symmetric matrix, check it this one that all the diagonal elements are positive or not, this all are positive, then proceed for the all leading minors must be greater than 0. So, all leading minors is order 1 is got 7 greater than 0, order 2 is we got greater than 0, order 3 is also greater than 0. That means, what you can say, this we can say that P is a positive definite matrix. Once P is positive definite matrix, we by definition we know x transpose P, x transpose P x is always greater than 0, this x transpose P x is always greater than 0. So, this function is a quadratic function is a positive definite matrix. Similarly, we can go for what is called positive semi definite. Agree? So, next class we will discuss positive semi definite and negative definite and negative semi definite, how to test using the Sylvester criteria, Sylvester criteria. Agree? So, thank you.